Good morning, everyone. Today we are gonna to learn about the regular-falsi method. In our previous video, we have completed the bisection method. Now we are moving toward regular-falsi method of finding roots. Now uh, came to the introduction of regular-falsi method. The regular-falsi method, also known as false position method, is a numerical technique for finding roots of equation. It is commonly applied to polynomial equations where analytical solutions are difficult to obtain. And their key requirements are initial interval or initial guess. Function that are initial guesses we have take must satisfy the following condition: f of a into f of b is less than 0. The sign change condition ensure that the root exists between a and b. As we have also discussed this in our previous video of bisection method, you will all can relate from that. Now, what is the objective of this method? The primary goal of regular-falsi is to find roots of equation where analytical solutions are difficult to impossible to obtain. Many real-world equations cannot be solved algebraically, making numerical method essential for approximating solutions. Though iterative refinements, the method progressively improves accuracy by narrowing the interval containing the roots. Each iteration brings the approximation closer to the true root value, continuing until the desired precision is achieved. Now, the formula of regular-Falsi method is formula equals to x a f of b minus b f of a divided by f of b minus a. In our previous bisection method, we used a different formula to convert them by half. With that formula is a plus b by 2. And now here there is a different formula which is given x equals to a f of b minus b f of a divided by f of b minus f of a, where a is a lower limit of interval and b is the upper limit of interval. F of a, f of b, function values at the endpoint, x equals to approximate root secant line intersection with x-axis. Now the advantages of this method is it is simple and easy to implement. Regular-Falsi use a straightforward formula that is intuitive and understand and code. It requires only basic arithmetic operations, making it accessible for students and practitioners alike. More efficient than bisection method is good from the bisection method. Unlike bisection method, which always halves the interval, regular-Falsi uses weighted interpolation based on the function values, often converging faster. Additionally, it does not require differentiation like a neutral Raphson method. Now, there are some low points also about the regular-Falsi methods that can have slow convergence in some cases due to stalling effect, where one endpoint remains fixed while the other moves very slowly towards the root. Requires an initial interval where the function changes sign f of a into f of b is less than 0, which may not always be easy to identify. Only applicable for continuous function or given interval. Discontinuous function may produce incorrect results or fail to converge. May require many iterations compared to fast methods like Newton-Raphson for certain function types. Now come to the problem statement or example. We have also done this example using the bisection method. Now we do the same thing using the regular-Falsi method. So the question is same: x square minus x minus 1. This quadratic equation that has one positive root approximately equal to 1.618, the golden ratio. We will use the regular-Falsi method to find this root iteratively. Now its initial values or initial guess or interval selection. As we have seen, what the condition is: f of a into f of b should be less than 0 or will be negative. So we can easily identify that one f of 1 or f of 2, any one value should be minus negative and one value should be positive. So here we choose the initial guess, a equals to 1 and b equals to 2, as we have taken in the bisection method, and evaluate the function, and it satisfies the value, so the root lies between 1 and 2. Now iterative iteration table, we have came in iteration 1. Here we put the value of a and b, and in function we have also put the value of a and b. Now solving the first iteration, we have got the value of x. Now we put value of x in the function and get the result. If the result is in the negative, then we change the value of a, and if the result is positive, then we change the value of b. Here we can see the in the first after the first iteration the result is minus 0.25, so we change the value of a. So our new interval is 1.5 comma 2. Since 1.5 comma 2 and f2 is less than 0, so we will go with that. Now iteration, and we will also compare this f of 1.5 with our error approximation. If it is less than that, then we can if it is less than that, then we can assume it is the final solution. Otherwise we will continue the iteration. Here it comes iteration 2, x equals to 1.6, f of 1.6 equals to minus 0.04, and the new interval is 1.6 comma 2. After solving this whole thing for this iteration, we will find 1.6, and this is the value. Here again the value is in minus, so we change the value of a. Now we come to iteration 3, where the value is came 1.615, and f of x, if we see, is less than our error approximation or tolerance, so we can assume it as a final solution, and the new interval is this. Root converging toward x, we can find the probable solution, as we have discussed here, that the solution would be nearby the golden ratio, that is 1.618. Now what the final approximation root? After several iterations, the approximation root converges into the golden ratio. This is very close to golden ratio, we can say. The method successfully converges to the positive root of f of x, x square minus x minus 1. Now near root estimation is 24.4, secant updation is 15.4, and you can go through all this data. Final approximation is there 42.3, which is good as compared to the bisection method. Also it only takes 3 iterations, as you see, and the bisection method takes around 7 iterations for the same value. And if we will increase our error approximation, then it will increase all the things. Okay, now we come for the algorithm. Here the algorithm, we will start with the start, and then input the initial values as done in the bisection. Now check the condition with initial values of sign change. Now we will put the new formula which I have got for the Regular-Falsi method, and compute the x. Now compare fx and compared it with the now compared it with the error tolerance. If it is less than, then the final value, otherwise it will we will do the iterations. Now update the interval on the basis of the signs, as we have discussed in our bisection method, how to change the sign and how to calculate tolerance and error approximation. So for that you will go through first with the bisection method. That will be good. Then we change the values of a and b on the sign of f of x. Now repeat this until the desired accuracy, or I have discussed about the tolerance and error approximation is got, and after that print the root and stop. Here the program with the algorithm. We will define the f of x, and in which the return the value of function. Here the argument passed is x. Now we will define another function. This is Regular-Falsi, where we can take these arguments and check the condition. If f of a or f of b is greater than or equals to 0, then we return null, that no root in this interval. If the condition is false, then we will go for the for loop, that is for I in range and max iterations. it is given 100. Now x equals to, we'll put the regular falsy formula, and calculate the value of x, and then after that calculate the value of fx. If the fx is less than the tolerance or error value, then we will return the x. Otherwise we will perform the iterations, compare the value with 0 of, for the change of value of interval f of a into f of x. If less than 0, then we will change the value of x, then we change the value of b. And otherwise, if the f of a into f of x is greater than 0, then we change the value of a and return the x. Now we will write the main program where root equals to regular falsy 1 comma 2, and print approximation root and root. So here is a program for regular falsy. You can go through it and practice it, and do certain questions which will increase your understanding. Now there is a flow chart, like we have discussed, as we have discussed previously in algorithm, and in program it's the same like that. That the start, input a and b, check the sign change and calculation x using formula, then evaluate fx, check if fx is less than tolerance, if yes, output x and stop. If no, update the interval, replace a or b based on the sign of f of a into f of x, and repeat the calculations. Now, what are the applications of regular falsi method? In engineering, regular falsi is used for solving non-linear equations in electrical circuit, mechanical system, and structural analysis, where analytical solutions are impractical or impossible to obtain. Scientific computation and numerical analysis, foundational root founding method used in simultaneous mathematical modeling and as a building block for more advanced numerical techniques. Now at last we come to the conclude the video. The regular falsi method is a robust numerical technique for finding roots of equation. It combines simplicity with better efficiency than bisection through weighted interpolation. This makes it an excellent choice for both educational purposes and practical computational applications. This method is effective for continuous functions where a sign change exists in the interval, ensuring convergence to the root. For example, f of x equals to x square minus x equals to 0. We successfully approximated the golden ratio through the iterative refinement, demonstrating the method's reliability and accuracy. Thank you, and stay connected for another for more NED updates. You can go through the bisection if you have not viewed that. Thank you. Have a nice day.